Look at this sequence here. It starts 1, 2, 4, 8, 16. What do you reckon the next term is? Some of you might reasonably assume that these are just the powers of 2, and so the next term should be 32. Many of you will have seen a certain 3 blue 1 brown video before and guessed that it's 31. This time though, the naive pattern seekers win because the next term in this sequence is 32. The one after that is 63 though. Bet you didn't see that coming, or maybe you did. It doesn't really matter. The real question should be, if this sequence isn't just the powers of 2, what is it? Well, if you have watched that 3 blue 1 brown video, you'll remember that the sequence goes like this. And what this is a sum of the first 5 terms of each row of Pascal's triangle. And this starts out looking like the powers of 2 because the sum of each complete row of Pascal's triangle is a power of 2, and for the first 5 rows, each row contains no more than 5 terms. In the exactly same vein, the sequence I showed you is the sum of the first 6 terms of each row of Pascal's triangle. And so that's a nice qualitative description, but this is a mathematical sequence. So what we'd really like is to have a closed general formula for the nth term. And to get that, you have to understand what the rows of Pascal's triangle and the numbers within them actually mean. Let's look at this row here, starting 1, 4. The numbers here are telling us how many ways we can pick 0, 1, 2, 3, or 4 objects from a collection of 4. And to get the actual numbers, we use the formula NCR equals n factorial over n minus r factorial times r factorial. Plugging our values in, we get that our 5 numbers are just 4 factorial over 4 factorial times 0 factorial, 4 factorial over 3 factorial times 1 factorial, 4 factorial over 2 factorial times 2 factorial, 4 factorial over 1 factorial times 3 factorial, and 4 factorial over 0 factorial times 4 factorial. And then, if we selectively cancel the numerator with the term on the left in our denominator, we get 1, 4, 4 times 3 over 2 factorial, 4 times 3 times 2 over 3 factorial, and 4 times 3 times 2 times 1 over 4 factorial. And hopefully you can see that if we'd started with the nth row instead of the 4th row, our first 5 terms would be these here. I'm not going to read them out, but you can see that each time we increase a factorial by 1 and multiply the numerator by n minus the next natural number. And what's cool is this really is true for any row. If we look at the second row, we get that the first 5 terms will be these, but 2 minus 2 equals 0. So the 4th and 5th terms are also 0. So we get the expected 1, 2, 1, and then I guess the 0 and 0 in brackets. And so, armed with this knowledge, we can start building up a table of expressions for the sums of the first k numbers in a row of Pascal's triangle. Okay, well, that works, but it would be nicer if we could write each of these as single polynomials instead. If we do this with k equals 3, we get 1 plus n times n minus 1 over 2, and then we pull out the factor of half and get this, and we end up with a half times n squared plus n plus 2. And then if we do k equals 4, we get 1 plus n times n minus 1 over 2, plus n times n minus 1 times n minus 2 over 6. And we already know what this bit is, we've just calculated it. And then we pull out the factor of a sixth, and ultimately we get a sixth n cubed plus 5n plus 6. And you could just keep on computing these general formulas, and there's nothing wrong with that, but it takes time, right? Surely there has to be a quicker way to do this, a general formula, as it were, to work out the values of these coefficients. Well, let's give it a shot. The first thing to notice is that the formula for the k plus 1th sequence can be written in terms of the kth sequence like so. You get that bk plus 1 equals bk plus x times x minus 1 all the way down to x minus k minus 1 all over k factorial. And we can make this look slightly cleaner with some snazzy product notation. And it's that second term that we need to focus on. We really need a clean and simple way of finding the coefficients of that polynomial. And when you're trying to do something like this, the best way to start is often just experimentation. If n equals 3, for example, then we're calculating x times x minus 1 times x minus 2, which ultimately is x cubed minus 3x squared plus 2x. But actually in this case it becomes a little clearer if we don't simplify it that much and instead leave it as x cubed minus 1 plus 2 times x squared plus 1 times 2 times x. So we can see that the coefficient of the second term is minus the sum of our roots, minus 1 plus 2, and the coefficient of the third term is the positive product of our roots, 1 times 2. And this is true for any polynomial. The coefficient of the second term will always be minus the sum of the roots, and the coefficient of the third term will be plus the sum of pairs of products of the roots, and the coefficient for the fourth term would be minus the sum of triplets of products of roots, and so on and so forth. These relationships are known as Vieta's formulae, and are something you can pretty easily verify if you just take, for example, x minus a times x minus b times x minus c, and just expand it. But for now, I just ask that you accept this is correct because I said so, and with this blind faith in me, we can draw up a table to see how the value of n affects the coefficients of various terms. There we go. Now our table is populated, we can start working out general patterns. Right off the bat, it's clear that the first term will always have a coefficient of 1. The second term, we're just adding up the first n-1 integers, which you could write in summation notation like so, and then that's just equal to n times n-1 over 2, and boom, we have our first meaningful progress, our first general formula. Alright, now let's look at the third term coefficients, just in isolation. Now let me rewrite them like this, and then like this. Now let's just look at the differences each time. To go from n equals 3 to n equals 4, we add 3 times the second coefficient when n equals 3. And to go from n equals 4 to n equals 5, we add 4 times the second coefficient when n equals 4. So our difference can be written as n times n minus 1 over 2, which you can rewrite in two useful ways. Firstly, as n times the sum of the integers from 1 to n minus 1, and secondly as n squared times n minus 1 over 2. And this second way lets us find the formula for the nth third term coefficient. It will just be the sum from 1 to n minus 1 of n squared times n minus 1 over 2. Now if we repeat this process for the two fourth term coefficients we wrote, we get this, which again we can rewrite differently like this. And as you can see, to get from n equals 4 to n equals 5, we add 4 times the third coefficient when n equals 4. And so our difference this time will be n times the sum from 1 to n minus 1 of n squared times n minus 1 over 2. And we could go on like this and calculate explicit formulae for the nth term coefficient for everything, but that takes ages, and with each new term the degree of the polynomial for calculating it increases by 2, so it gets very messy very quickly. And remember, these coefficients aren't even the final coefficients we're looking for. This is just one half of the formula. Instead, we're going to turn to drawing shapes. Just one shape, actually. A shape that is wonderfully ironic given this question's roots. The shape starts with a 1. And this one passes down a copy of itself to the left and the right. And these two new ones pass down a copy of themselves to the left and a copy of twice themselves to the right. For the numbers in this row, they pass down a copy of themselves to the left and a copy of 3 times themselves to the right. And we continue as we move from the n to the n plus 1th row. Each number passes a copy of itself down to the left and n times itself to the right. And there we go, Pascal's triangle deluxe. Well, almost. We've been conveniently ignoring the minus signs up until this point, but luckily everything works out really nicely and we can just change add n times itself to the right to add minus n times itself to the right, and voila, the real Pascal's triangle deluxe. TM, yes, I am trademarking that. And now we can start cooking up our polynomials, finally using the formula from decades ago. We start with our degree 1 sum of 2 terms polynomial, x plus 1. And then we double it to account for taking the half out, and then we can just do column addition with the next row. So we'll have 2x plus 2 plus x squared minus x, which gets us x squared plus x plus 2. And then of course we can't forget about the half we just had, so we stick that out at the front, and as before we get a half x squared plus x plus 2. And to get the next one, we triple what's inside the bracket, column addition it with the next row, and then plonk the 1/6 on the outside. And again, as expected, we get a 6th x cubed plus 5x plus 6. And you can just do this on repeat, multiplying what's inside the bracket by n, adding the nth row of the triangle, and sticking a 1 over n factorial on the outside. And I wasted a solid 15 minutes of my evening writing a program to do this, right? I haven't used Python in like 8 months, so I had to really lock in to get these like 30 lines of code, so you'd better subscribe. But I did calculate the coefficients up to a degree 31 polynomial. The one I'm showing you here, however, is just a degree 15 polynomial. Alright, fine. So we didn't actually reach a general formula per se, but we do have a general algorithm for producing the formulae for these bait sequences. Now let's look at the graphs. And these should be interesting because we know that for a certain interval, they match 2 to the n exactly when n is an integer. But what about between integers? It surely can't be a perfect fit, otherwise we've just bettered a tailored series, which would be kind of crazy. But how off is it? Well, it's this off. Let me zoom in a little so you can see properly. There is a small difference. It becomes more and more apparent the further you stray from an integer, but all things considered, this is a damn good approximation. It's so good, in fact, that we can use it to try and approximate the natural log of 2. How? Well, the derivative of 2 to the x is 2 to the x times ln 2, and for our approximation b of x, we can also work out its derivative, and over the interval where our trick works, these two should be the same, roughly. So we get that the natural log of 2 is approximately b prime of x over 2 to the x. Using our degree 6 polynomial and evaluating at x equals 4, we get that the natural log of 2 is approximately 133 over 192, which is correct to 3 significant figures and gives us 0.693. And the crazy part about this approximation specifically is that this could have been done by hand, from start to finish, in maybe like 20 minutes. So this really could have been a viable way to approximate the natural log of 2 back in the day. I tried a few more approximations with the various polynomials I'd calculated, and the best I could be bothered to find was setting x equals 10 with the degree 15 polynomial, which gave me the natural log of 2 correct to 7 significant figures. I got 0.6931471,957, when it should be 0.6931471,806. Well, that's the yapping for today. You can now fool your friends and approximate the natural log of 2. If you enjoyed, please subscribe. This is the most thinking and planning and experimenting I've done for a video yet, so it would mean a lot to me. And, of course, thanks for watching.